Water at 1000 kPa, 250 degrees Celsius, is brought to saturated vapor in a rigid container. Find the final T and the specific heat transfer in this isometric process. Given, in state 1, pressure is 1000 kPa, temperature is 250 degrees Celsius. It is under isometric process going to state 2, which is saturated vapor. Solution: LCM, M1 equals M2 equals M. FLT, delta U equals Q. SLT, delta S equals QT. In state 1, pressure is 1000 kPa, temperature is 250 degrees Celsius. It is superheated vapor. From table B1.3, U1 equals 279.91 and specific volume is 0.23268. State 2, volume 1 equals volume 2, which is 0.23268. It is a saturated vapor. By linear interpolation, we can get U2, which is 2577.914. By linear interpolation, from table B.1.1, temperature will be 171.95 degrees Celsius. From FLT equation, delta U equals Q, and substituting the values, specific heat will be negative 131.996 kilojoule per kilogram. So, the final temperature is 171.95 degrees Celsius and the specific heat transfer is negative 131.996 kilojoule per kilogram.
An air conditioner provides 1 kg per second of air at 15 degrees Celsius, cooled from outside atmospheric air at 35 degrees Celsius. Estimate the amount of power needed to operate the air conditioner. We are given with mass flow rate at 15 degrees Celsius and said that it was cooled from outside atmospheric air at 35 degrees. We are asked to calculate the power needed to operate the AC. Using the coefficient of performance of refrigerators, we can calculate the power needed. However, heat transfer of air is not given along with the coefficient of performance. But heat transfer of air is equal to its change of enthalpy, where we can express as Cp dt. The value of heat transfer is 20 kilowatts. Also, the coefficient of performance can be expressed in terms of temperature, since engines have equal efficiency with temperature if they operate between same heat reservoirs. Thus, substituting the given temperature will result to 14.4. The needed power is equal to the ratio of heat loss by the engine to coefficient of performance, which gives 1.39 kilowatts.
Problem: 1 kilogram of water at 300 degrees Celsius expands against a piston and cylinder until it reaches ambient pressure, 100 kilopascal, at which point the water has a quality of 90.2%. It may be assumed that the expansion is reversible and adiabatic. What was the initial pressure in the cylinder and how much work is done by the water? Given, at state 1, temperature is 300 degrees Celsius. At state 2, pressure is 100 kilopascal and the quality of water is 0.902. The assumptions are: process is reversible and adiabatic, therefore heat transfer is equal to 0 and change in entropy is equal to 0 as well. For the equations to be used in this problem by law of conservation of mass 1 is equal to mass 2. By first law of thermodynamics, mass times the change in internal energy is equal to heat transfer minus work. But since Q is 0, mass times change in internal energy is equal to negative work. And lastly, by second law of thermodynamics, since change in entropy is 0, S1 will be equal to S2. At state 2, pressure is given and quality is given as well. So by using table B.1.2, entropy could be solved as 6.7657 kilojoule per kilogram Kelvin. Internal energy can be solved as well as 2301.36 kilojoule per kilogram. At state 1, temperature is given and entropy is known since S1 is equal to S2. By using table B.1.3, it could be found out in the table that pressure is 2000 kilopascal and internal energy is equal to 2772.56 kilojoule per kilogram. Going back to the first law of thermodynamics equation, the values are to be substituted, giving work as 471.2 kilojoule. Therefore, the final answers are: pressure is 2000 kilopascal and work is 471.2 kilojoule.
A steam turbine is an inlet of 2 kilograms per second water at 1000 kPa and 250 degrees Celsius with velocity of 15 meters per second. The exit is at 100 kPa, 150 degrees Celsius and very low velocity. With the room temperature at 20 degrees Celsius, find the power produced and the irreversibility of the process. So we are asked to find the power and the irreversibility. We know that 2 kilograms per second of steam entered a turbine at 1000 kPa, 250 degrees Celsius at 15 meters per second, and it exited at 100 kPa, 150 degrees Celsius with very low velocity. Assuming that the process is adiabatic, we start off with the law of conservation of mass, which tells us that mass at state 1 would equal to the mass at state 2. And we now establish the first law of thermodynamics equation and also the second law of thermodynamics equation. At state 1, since the P saturation is greater than the pressure given, then the steam is superheated, and from the table, we can get the enthalpy and the entropy. And at state 2, since the P saturation is also greater than the pressure, then the steam is superheated as well, and we can also get from the table the values of enthalpy and entropy. Substituting the values to the equation, we can now calculate for the power, which would give us negative 764 kilowatts. And to calculate for the irreversibility, we first calculate for the entropy generation, and by multiplying that to the temperature, we would get 183 kilowatts.